Okay, so it's my pleasure to introduce Mark Selke, who was my intern last summer and who is my intern again this summer. He's also a grad student at Stanford, and he's going to tell you about both a breakthrough paper, solo papers that he had, but also some joint work that we had in the lab. So with particularly Yin Tat Lee and Yuanji Lee, who are also both previous interns, so there is a lot of emulation going on in the group. It's really great. And Boaz Klartag, who is actually the advisor of Ronan Eldan that you're going to hear next. Okay, I leave it to you, Mark.
Okay. Cool. Thanks, Eb. So yeah, this is largely from my internship last summer. I'm going to tell you about chasing convex bodies. Cool. So first, let's say what the problem is. So we're given a sequence of convex sets in d-dimensional space given by an adversary. After we receive the teeth set, we, the algorithm, which I'll call alg, are going to pick in real time online a point in the set, and we're going to move to that point. Seems pretty easy. What we want to do is minimize our movement. So we'll just say we start at the origin, and the total cost of the algorithm after big T time steps is the sum of the distance we moved every time we moved. In some norm, which you can just think of as Euclidean norm, but you could do this in some other norm or something too. We're trying to minimize our movement, but it's not clear what that means. So we need to pick a benchmark to compare against. The benchmark we compare against, which we'll call opt, is the offline optimum. What that means is opt gets to see all big T sets in advance and just compute the best path. So we are playing in real time, but we're comparing against the best possible solution who's not in real time and can therefore make better decisions by planning ahead. We're going to aim for a multiplicative guarantee, which people call a competitive ratio. So we'd like to ensure that our cost divided by the best cost we could have had in hindsight is bounded by some constant, which could depend on the dimension, but should not depend on like big T, or should not depend on the request sequence. So this constant alpha is called a competitive ratio if we can achieve it. The problem is, can we achieve a finite competitive ratio? How small a competitive ratio can we get? Does this make sense so far? Awesome. So here's an example with 3 requests, just to kind of give you a picture in your head. So we start at x0 over here. The first request we see is going to be a line, and the alg in red is just going to move to the closest point. Opt is going to move to the side, and we're not really sure why yet. And notice when we actually are acting as the algorithm, we don't see where opt is. We just see the requests. So opt here is kind of secret. Here's another request. We still don't really know what opt is doing. Here's the last request. OK, now we see what's going on. Opt was just moving to the closest point in the last request set, K3. And alg did a little bit worse, but maybe not so much worse. It looks like we're in a factor of 2 or so. Cool. First, let me tell you about 3 motivations for this problem. There are a lot of ways to kind of describe another problem that looks very similar to this problem and kind of motivate it from a bunch of angles. So the first one is more of a pure math motivation. The idea is, in general, you could think about, and people have thought about, selectors, which are functions that just take in a set and output a point inside that set. There's kind of no online component here. And the problem is to find selectors that are Lipschitz. So a problem that you could think about, and mathematicians have thought about, is can I find a selector that takes in an arbitrary convex set, outputs a point in the set, and has some sort of Lipschitz property. So if I change the set a small amount, then the point outputted doesn't change too much. OK, Lipschitz doesn't mean anything unless I have a metric on sets, and we're going to use this Hausdorff metric. OK, there's 2 definitions. The first one's maybe a little bit easier. It's just the max distance from a point in one set to the other set. And you have to look at it in both ways. So OK, we have some metric on sets. We want to pick a point in the set that doesn't move too much. And you can kind of think of like this Hausdorff distance is like the cost of opt if we kind of first get the request k and then the request k prime, and we're thinking, okay, for the worst point in k, what's the amount of movement we'd have to do? And this Lipschitz constant is like how much are we moving compared to that. So chasing convex bodies is sort of this natural geometry problem, but with an online real-time sort of component. There's two more motivations, and to explain them, I should first talk about an equivalent but seemingly more general problem called chasing convex functions. So it's a similar problem, but instead of receiving convex sets, we receive positive convex cost functions. And we again pick our new location after seeing the function. We pay the same movement cost, but we also, for every function, pay ft of xt, where we pick xt after observing ft. So it's very similar, except instead of kind of a hard constraint that you have to be in the set, there's a soft constraint where you're penalized by this function. And you're again trying to get within some bounded multiplicative factor of the best solution that gets to see the functions in advance. It turns out these problems are actually equivalent, and showing they're equivalent is much easier than solving either one of them. It's kind of easy to view a convex set as a function. You can just make the function 0 on the set and really big outside. To go the other way, there's something you can do where you take the region above the graph of the function, where you go up one dimension. It's pretty simple if you think about it for 30 seconds. So the second motivation is another well-studied problem called metrical task systems. You can think, OK, I have an arbitrary metric space x. I have an arbitrary set of permitted positive cost functions. I'm trying to move around to minimize my total cost, so it's the same problem. And so the question is, like, what kind of competitive ratio can we get? How does that depend on the metric space and the cost functions? This has a lot of different types of applications. And in a worst case, if there's no restriction on the cost functions, the competitive ratio is something like log n for a metric space with n points. So here we have an infinite metric space. So OK, this is telling us we can get infinity, which is not so good. But we have a restriction on the set of cost functions, so we can hope that that makes the competitive ratio finite. There's a famous problem in computer science called the K-server problem, which where a similar sort of phenomenon happens. You might expect it to be infinite, but it's finite because there's a restriction on the set of cost functions. So from this point of view, chasing convex bodies or chasing convex function is asking, like, how does convexity affect the complexity of this kind of task system problem? The third motivation is online convex optimization, which is maybe related to the convex optimization or the bandit classes you guys had last week. So let's assume the functions are 1 Lipschitz. This is a pretty mild assumption. Then we can think of the movement cost as an upper bound for the advantage we get by looking ahead one time step. In a lot of, like, in sort of bandit type of problems, you usually pick your point and then you see your loss function. But if it's kind of just by definition, just for every t, that inequality is true and I'm summing over t. So I can think of the movement cost as just accounting for the fact that I get to see my function before I pick it, before I pick xt. OK, so there are a lot of works on regret guarantees, and even for convex functions, even with bandit feedback, you can get this sort of guarantee with a root to regret. But what if the optimum can move? So for chasing convex functions, we allow a moving optimum. Here, we're looking at the minimum single point x as our benchmark. So we're thinking of the best optimum that just stays in one place. If we think the world is kind of non-stationary, then it makes sense to try to do well if there's any moving policy that does well, and then you get this sort of problem naturally. I'll just mention, it's been studied under the name smooth online convex optimization in kind of robotics, control theory types of papers because of this sort of connection. OK. Any questions so far? Yeah.
In this problem setting, do you get to see FT and then you're picking, or is it banded in the sense that you pick something and you only really get to see the value fx? Because if it's banded, it seems impossible to compete against a moving.
Yeah, that's a good question. So I think if you just have bandit feedback, that won't work. I think like if you get to see the value and the gradient at the point you pick, then it ends up being OK because you can just kind of pretend the function is the linear function with that gradient and that value, and you get roughly the same thing. Yeah. Did I answer your question? Cool. Any other questions? Awesome. OK, so let me tell you about some previous work on this problem. So the problem was first introduced in the early 90s by Friedman and Linial. So they posed this general problem. They gave a competitive algorithm in 2 dimensions, which you might think should be pretty easy, but is actually not very easy at all. They really had to do some tricky stuff. They also gave some lower bounds, which are basically the best ones we know still. So in Euclidean space, you can get a square root d lower bound in d dimensions. In d-dimensional L infinity space, you get a lower bound of d, which is the best you can get in an arbitrary d-dimensional norm space, which is why I'm mentioning it. Both of these are pretty simple. You just kind of start with a hypercube, and you kind of every request fixes the value of like 1 coordinate at a time. So you're kind of shrinking down to a point. Anyway, it's like pretty basic. It's kind of very, very like primitive almost compared to like, I mean like the problem like there wasn't really much more progress on this problem, and this lower bound is so simple. So it kind of got revived kind of recently. So a couple of other papers that looked at it showed that if all your subsets are hyperplanes or other subspaces, then you can get a finite competitive ratio, but it's exponential. And a couple of more applied robotics-y people at Caltech showed that if all of your cost functions, if we're looking at the function point of view, if all the cost functions are strongly convex, then you get a dimension-independent competitive ratio just depending on how strongly convex they are. So I guess there are plenty of applications where that is, you're kind of happy with that. You don't care about functions that are kind of flat for a while, or like a body. Another observation I want to mention that makes this problem a lot easier to think about is that there's a couple different ways that we could set up the problem. One of them is that we have to have an algorithm that can do well even if the adversary, the request sequence, can depend on what we're doing. Another one that you often see in bandit literature is the adversary has to fix his request sequence ahead of time, and then you can use randomness. So maybe it's easier to give a random algorithm that does well against any fixed adversary, this oblivious adversary model. Maybe that's easier than giving a deterministic algorithm that has to do well against an adaptive adversary. But for this problem, they're actually equivalent. And the reason is that if you have an oblivious adversary, so the adversary fixes his request sequence beforehand, if you're using randomness, I can make a better algorithm by just averaging all of your randomness into a deterministic path. And that just, these convex sets are convex, so if I average any paths, they're still valid, and the movement ends up decreasing on average. So we can just assume we have deterministic algorithms. That means the adversary can adapt to us in real time, so any guarantees we get are going to have this, they're going to hold in this pretty strong sense. Yeah?
There's a result for strongly convex functions.
Yeah.
Is there an equivalence for these convex sets?
Yeah, I don't think so. I mean, like if you're, like plenty of applications, you probably are just happy to only consider strongly convex functions. But I mean, when you reduce from a body to a set, you're getting when you reduce from a convex set to a convex function, you're directly making the function that's like 0 on the whole set. So it's very not strongly convex. Yeah. So I think this problem is actually easier.
The question was the other way around. Like, is there a restriction on convex sets which would correspond to strongly convex functions?
I see. No. Not that I know. Yeah. In a sec, we'll look at a different restriction for convex bodies, which ends up being a great stepping stone to the full problem. But I think I don't think there's a nice set version of that assumption. Any other questions? Cool. Yeah, great, next slide. So chasing nested convex bodies is a restricted case of the problem that ended up helping us a huge amount in solving the full problem. So this is the restriction where the first set is the biggest, and then the sets just shrink down over time. All they can do is shrink. Like in the picture there, they're kind of getting lighter as they get smaller, and we're moving kind of inward. This condition means that the cost of the opt is just the distance from the starting point to the current request. So the opt has to start at the same starting point, and then at any time, the best thing for him to do is just move all the way to the latest request because of this containment. Actually, the nested problem, you can simplify it a lot because I don't want to spend too much time on this, but basically you can just treat it as a separate problem that resets every time this distance to the current set goes up by another factor of 2. And so because of that, you can just say you start with a ball, you don't care about opt, you just want to move as little as possible for a sequence of shrinking requests that start from a ball. Basically, if you're starting from a ball, then opt is kind of 1, even though opt might not actually be 1. But if you do this kind of resetting every time, then you're always at a reasonable scale. OK, I don't want to talk about this point too much, but it simplifies the problem a lot. So this problem does turn out to be easier. It turns out if you just do greedy, so you just keep moving to the closest point in the next request from where you are right now, then you get an exponential competitive ratio. This is actually interesting because it's equivalent to just thinking how long can the path of gradient descent go if you stay in the unit ball. It's kind of a pretty natural question in its own right. But there's nothing like this for the general problem. OK, so last summer, we had this kind of bare hands recursive approach to chasing convex bodies. It makes more sense in the nested case. So I'll tell you about that for a little bit. The idea is, let's just say we're in the middle of the current request. So if we're in the middle and we're forced to move, then the next convex set is kind of all the way on one side. And since we're in the middle, we can hope that that means the next body has to be a lot smaller than the current one. Kind of, it's kind of some sort of like high-dimensional binary search, which is kind of going in all directions at once. And there's a theorem that tells you something like this. If you're at the center of mass, then every time you're forced to move, the next request went down in volume by a constant factor. This is some really cool convex geometry theorem called Grunbaum's inequality. So what you can hope is, let's say the volume goes down by a factor of 2 to the d, because we did like d steps of this. If the volume went down by 2 to the d, that sounds like the diameter went down by a factor of 2. If the diameter is going down by a factor of 2 every d steps, then we're only going to have like order of d movement, because the problem scale is just shrinking really fast. So that's what you hope for. It doesn't work as stated, because like here, I'm chopping off this top part, which is like red, and I just have this smaller thing down below left. The volume shrank by a lot, but it stayed long in one dimension, and it could just keep getting thinner and thinner and staying long. So you can't do this. But there's some trick you can do where you can say, I'm going to look at the short and long dimensions separately and kind of only move in the short dimensions as long as the long dimensions stay long. So there's some trick that makes this basic idea work. What results can you get? So This first paper introduced the idea and got a sort of d log d competitive ratio in any norm space with dimension d for nested chasing. One of our papers last summer refined this by taking a weighted center of mass. And so we got square root d up to a log factor in Euclidean space, so matching the lower bound up to this log factor. Also, it's optimal up to some log factor in any LP space, which is pretty nice. And then we tried to use it on the full problem, and we got an exponential competitive ratio. So this was the first exponential competitive ratio in more than 2 dimensions. But I mean, sorry, the first finite competitive ratio in more than 2 dimensions. But it's kind of inefficient and complicated. It's sort of like you break up into phases. In each phase, you kind of pretend you have a nested problem. You have to induct and recurse on both the like size of the problem and the dimension. So you get some exponential dependence. So that's what this bare hands approach gives. Any like kind of big picture questions about this approach? Cool. So for the last 10 minutes or so, I'll try to tell you about this new approach based on the Steiner point, which is this. Well, to me, it seems kind of magic. It's a selector that just kind of does everything you want for this problem. So let me tell you some background. So we actually know, so it's some selector. It just inputs a set, outputs a point in the set. It has the exact minimum Lipschitz constant among selectors. And this turns out to be order of root d. I can say more about exact minimum afterwards or offline if you're curious. It's kind of, it's really magic. So in this same nested paper last summer, we analyzed the Steiner point, and it actually has competitive ratio d. And in fact, if you only have t requests, then you can get a competitive ratio of square root d log t. So unless you have like an exponentially large number of requests, you're basically matching this root d lower bound. Okay, in fact, it's the exact optimal memoryless algorithm for any D&T, kind of analogously to being the exact minimum Lipschitz constant selector. So this is the best memoryless algorithm, but this bare hands approach did give a better competitive ratio that didn't depend on T by using a memory in some way. That's kind of an interesting separation. And just in May, me and 4 people from Carnegie Mellon independently extended this thing to the general problem of chasing convex bodies. And we basically get the same d or root d log t competitive ratio for the general problem by kind of taking the Steiner point and generalizing it to a convex function instead of a convex set. Yeah, so I'll try to tell you about that. Do people have questions about the results I stated?
About Steiner points, are they computable in any efficient manner, or is this like a crazy hard thing to compute?
So I'll show the definition on the next slide. I mean, so it's some integral average thing. So I guess you would try to compute it by some sort of Monte Carlo thing. Yeah. I mean, you're averaging a bunch of answers to convex problems. So I mean, that makes it sound reasonable. Yeah.
So do you expect the competitive ratio to have to depend on T?
Yeah, we're not sure. I mean, you know, it wasn't known if it was finite a year ago. So yeah, we don't know. I mean, that's a good question to remove this T dependence. Yeah, in the back.
You might have said this in an answer to another question. Is there like a short explanation of what a Steiner point is?
Yeah, it's on the next slide.
Okay.
Yeah, hold on for 1 second. Yeah.
Is the thing above also minimum d, and it says exactly d, and then it says it's root d log t?
Yeah, so what that means is if T can be arbitrarily large, then you get D.
Okay.
But if you fix some T, which is not very big, you might get something better.
So then it's the second one.
Yeah. Like usually when you talk about competitive ratio, you're allowing T to be kind of big. Okay, so let's look at the definition. Kind of scary, maybe. So let's say we're in Euclidean space. There's 2 different definitions, and it's important for the proofs that there's 2 definitions. So they're in different colors. The first one is maybe easier to understand. So okay, first off, I have these integrals with a bar through them. By that, I basically mean expected value. So I have an integral, but I'm normalizing, so I'm integrating with respect to like a probability measure. So for this first one, I take a random vector v in the unit ball, and I compute f sub k of v, this argmax, which is the furthest point in my set k in the direction of v. And then I average that over the random choice of v. I'll just skip to the next slide where there's a picture. So what I'm doing here is I'm picking a bunch of vectors v. For each one, I'm associating with them the point in the set that's furthest in that direction. Then I'm computing this average. So because I'm averaging a bunch of corners of the set, I'm always in the set. Does that part make sense? Maybe. OK. The second definition is similar. There's this function hk, which is like how far in this direction. So I'm calling it theta instead of v just because theta is on the unit sphere instead of in the unit ball. But they're kind of the same otherwise. Hk is how far am I in that direction. And that's a number, but I multiply it by the input vector, and then I integrate that, and then I have this factor of d. That's maybe a bit more mysterious, probably harder to visualize. So there's two definitions. Yeah, maybe I'll just keep going. Yeah, this function is called the support function, kind of a important thing in convex geometry. Why do they agree? Basically, the reason is that f is the gradient of h, and theta is the outward normal to the sphere at theta. So there's some general version of the divergence theorem called the Gauss-Green theorem that just tells you this. Yeah, the factor d is because I made these probability measures, but the total measure of a sphere and a ball are different by a factor of d. Like 4 pi r squared versus 4/3 pi r cubed. OK. Let's see why Steiner point is a Lipschitz selector. So okay, basically I have these two definitions. The red one, it just tells us that we picked a point that's actually in the set. The yellow one is how we're going to control the movement. So to see that the Steiner point is Lipschitz, you just use the triangle inequality, and you are immediately done. So this Hausdorff distance I mentioned earlier is the exact same as the L infinity distance between these support functions. And so it's just one line triangle inequality. That gets you a factor of d. If you're a little smarter about it, you can get a square root of d by kind of saying that your integral is kind of pushing in a bunch of different directions theta, but they can't correlate very much. They're kind of going in all directions at once. How do you chase nested bodies? When you're nested, the support function decreases over time. So when you do the triangle inequality, there's no absolute value around here. And so you get a telescoping sum. And that's the whole proof. And OK, there's some way to get a root d log t if you use the right concentration inequality. How about for general bodies? So there's this thing called the work function, which appears in basically any online algorithm problem. It just computes the minimum cost of any path surfacing the request so far and ending up at the point x. And x can be anywhere. It doesn't have to be in the body because we can move there after servicing the last request. This is a convex function because I can do this averaging of paths, and it's Lipschitz. So basically what we're going to do is we're going to generalize the Steiner point to this work function. The idea is just if you think of a convex set as a function by making it 0 on the set and big outside, then I can recover these extreme points, these corners, by looking at tangent hyperplanes to this function with different slopes and seeing where they're tangent. And this support function h ends up corresponding to how high up they are. So you just kind of write down the analogous definitions, and OK, the same sort of thing works. In one dimension, there's a really nice picture, which is just you take the tangent lines with slopes plus and minus 1, and you see where they intersect, and that's the Steiner point. the only way it's moving is that these lines are moving upward because this work function is increasing over time. So the amount of movement is kind of clearly bounded by how much these lines are moving upward. Also, if the lines move upward, then their intersection point moves upward. Since the lines are a lower bound for the work function, that means the cost of opt has to be large when the lines are high. That's kind of what's happening, and you can turn the same triangle inequality proof into a proof here. Yeah, maybe a couple more things to mention. You can also get the same definition by taking a large level set. So the set of points where the work function is small, that's a convex set. You can compute the Steiner point of that set, and you get the same thing. That's what this other paper by this group from CMU did, actually. They just did this definition directly. You can also chase convex functions directly. So I kind of outlined some ad hoc reduction from chasing bodies to chasing functions, but you can just do the same functional Steiner point on the work function for chasing convex functions directly. In other norms, you can define the functional Steiner point. You have to think about what the divergence theorem means if you're not in Euclidean space, but it works. It's still d-competitive. This thing with the log t depends on some sort of concentration of measure thing, so it doesn't work in other norms. Some open questions. First, a great one is to fix this root log t gap. So for LP, where p is bigger than 2, the only gap is in this root log t. When p is less than 2, you actually have a polynomial gap. This is just based on comparing LP to L2 and saying they differ by a most factor of something. It would also be really interesting to try to go further and understand if there's function classes that are only a little bit non-convex that we can do, or more generally, what makes a problem of this sort easy or hard. Yeah, that's it. Thank you.